Okay, so in this video, we're going to be introducing some more terminology related to the Laplace transform, and that is the notion of causal and anti-causal Laplace transforms. Okay, so we're going to be talking about what these words mean in this video. Okay. So the actual definition for the words isn't going to come till the end. We're going to start with an example. Okay, but through the example, you'll come to understand what these words mean. Okay, so let's just recall what we saw before. We saw the Laplace transform, okay, of this function, e to the negative at u of t. We saw the Laplace transform. I'll put a little L here, but in the future, when it's obvious we're talking about Laplace transforms, I'm just going to use the double arrow. Okay, so we saw that this was the Laplace transform, and we also saw the region of convergence was when the real part of S is greater than the real part of negative A. Okay, so we derived that, okay, in a previous video. So now, let's derive another one. So now, let's find the Laplace transform of, okay, we're going to look at a new signal. It's going to be x of t, and here's what it's going to be. Negative e to the negative at u of negative t. Okay, we're going to derive the Laplace transform and the region of convergence of this function right now. And you'll see that it's very related to the Laplace transform pair at the top. All right, so Laplace transform x of t, we know what it is. It's the integral of our x of t function times e to the negative st dt. Okay, now what can we do? Well, I'll take the negative outside, and then this unit step of negative t, u of negative t, that's just a unit step function flipped across the vertical axis. So now this equals 1 when t is between negative infinity and 0, and equals 0 when t is between 0 and infinity. So since it equals 0 when t is between 0 and infinity, that's just going to zero out this entire integrand. I might as well not integrate over it. I'll just go from negative infinity to 0. That's where u of negative t equals 1. And what am I left with? I'm left with e to the negative s plus a t dt. Okay, now we can do this integral. So when I bring this negative down, it's going to cancel that negative. So I'm going to get 1 over s plus a times e to the negative s plus at, negative infinity to 0. Okay, so I'm going to get 1 over s plus a. When I plug in 0, I get 1. And then minus, when I plug in negative infinity, the negative there cancels, and I get e to the s plus a. And I'll just write it as infinity. Of course, I mean the limit as t goes to infinity here. Okay, so now we got to try and understand, when does this actually converge to something? And this was in that complex exponential, limits of complex exponentials video. Okay, we saw that this goes to 0, provided, what did we need to happen? We needed the real part of that exponential, okay, to be negative. We needed the real part of s plus a to be negative. Okay, i.e., what does that mean? In other words, okay, the real part of s plus a, as we saw before, we can break this up into the real part of s plus the real part of a, and then just bring the real part of a to the other side. Okay, so we get that the real part of s has to be less than the real part of negative a. Okay, I encourage you to, look at all of these properties involving real parts of complex numbers. You can prove them all easily using the rectangular form, for instance, of complex numbers. Okay, so you can kind of manipulate them in this way. So real part of s plus a is the real part of s plus the real part of a. You bring the real part of a to the other side, and it becomes the real part of negative a. Okay, so as long as this condition's true, what do I get for this function up here? I just get 1 over s plus a, right? Because this term is now going to 0, and I just have 1 over s plus a times 1. Okay, so that's what I need to get that equality there. Okay, that's my condition. And so that gives us our Laplace transform and our region of convergence. So negative e to the negative at u of negative t as Laplace transform 1 over s plus a. Okay, and the region of convergence is the real part of s is less than the real part of negative a. Okay, so what does this look like? It's the real part of S, it's the imaginary part of S. Okay, and I don't know, I'll just put a random A point there. Let's say that's A. Okay, then negative A here would be right there. We need the real part of S to be less than the real part of negative A. So I can draw this little dotted line at the real part of negative A. And the ROC is going to be on this side. Okay, so this is my ROC. Okay, sometimes people also plot the poles. So we can say what values of S make the magnitude of this Laplace transform go to infinity. Remember, that's what we called a pole. Clearly, there's a pole at S equals negative A, right? Because when S equals negative A, this denominator goes to 0, so the whole thing goes to infinity. Sometimes people mark the poles with X's. So I'll just do that here. Maybe I'll start doing that in the future. Okay, so there's a pole at S equals negative A. But sometimes people mark the poles in the S plane, this complex plane of all the values of S, they mark them with X's. All right, so that's what the region of convergence is, but wait a second, you might be remembering, look at this, I can put them on the same page. The Laplace transform of this function is 1 over S plus A. The Laplace transform of this function, wait a second, it's also 1 over S plus A. So how can we tell the difference? Well, this is why regions of convergence are so important, right? Because look, their regions of convergence are different. So that's how you can tell the difference. So the Laplace transforms themselves are the same. They're both 1 over S plus A, but they have different regions of convergence. Okay, so this is an important point. So e to the negative at u of t and negative e to the negative at u of negative t have the same Laplace transforms, but different ROCs. Okay. So in particular, let me just make this point here. You can't actually answer this question. You can't answer the question, what is the inverse Laplace transform of 1 over S plus A? You can't answer that question, right? Because if I just told you that 1 over S plus A, you'd be like, well, I don't know which function it is. I don't know if it's the one on the top or the one on the bottom. They both have that Laplace transform. Okay, so you can't answer that question unless you know the region of convergence of that Laplace transform. Okay, so you need to know the region of convergence in order to figure out which function produced that Laplace transform. And these two cases, right, these two functions that we have here that have the same Laplace transform, they're actually words, they're names for them. And here finally is the definition for those words I said at the beginning. So they are names for the two cases. Okay, so they're called the causal and anti-causal Laplace transforms. That's one piece of terminology that a lot of people use, but some other people also just say right-sided and left-sided. Okay, so you can see, so let me just say in this example what it is, and we'll talk about it some more. So in this example, okay, e to the negative at u of t is causal. And negative e to the negative at u of negative t is anti-causal. Okay, so we have these words causal and anti-causal, and causal, another way you can refer to those functions is by saying right-sided and left-sided. And those definitions probably could make more sense, especially in this context, because if we just look at what these two functions actually look like, right? Let's say this is our e to the negative at u of t, so it's 0 when t is negative, and equals this decaying exponential when t is positive. Okay, this is what we call a right-sided signal, okay, which you can kind of see just from the picture, okay, because it's 0 to the left, all the non-zero values for the function go off to the right, And similarly, if I were to draw this function on the left, okay, it's going to be 0 on the right and be, I don't know, some exponential function on the left. Okay, and this is what we call left-sided, because you can see it is 0 to the right and the non-zero values are to the left. Okay, so this is our left-sided function. Okay, so we might use words right-sided, left-sided. We might use causal, anti-causal. You'll see both of them. Okay, and so this is what they mean. So just to summarize, everything we did in this video. So this is an important point. We'll see this come up not just for these pairs of Laplace transforms, but for other ones as well in the next video. So certain functions, as we can see, have the same Laplace transform. And so how do you tell them apart? Well, you look at their regions of convergence. Okay, and that's how the Laplace transforms can differ. The Laplace transforms themselves are the same, but the regions of convergence are different. So that's how you'll be able to tell these functions apart. Okay, and we gave different names to those functions in time, either causal, anti-causal, or right-sided and left-sided. Okay, so we'll see more examples of this in videos to come. But that's all I had for this video. I will see you in the next one.